Let's put all the integers together. The goal here is to come up with a sequence that mentions every single integer. But before we do that, let's first try to come up with a sequence that mentions every non-negative integer. It's the sequence a sub n equals n, where the index n starts at 0. So the terms of the sequence are 0, 1, 2, 3, and so on. And of course, I could negate that sequence to get a sequence that mentions every negative integer. So I could look at the sequence b sub n equals negative n, but let's start n at 1. And if I do that, then the terms of this sequence start minus 1, minus 2, minus 3, minus 4, and so on. But I want both. I want a single sequence that includes among its terms every positive integer, every negative integer, and 0. Is it even possible? Yes, I'll weave together the two sequences that we've already built. So what do I mean? Well, let's take a look at these two sequences. I could put them together, right? I could weave them together. I could start with 0, then do minus 1, then minus 2, then minus 3. Right? I get a new sequence that would end up mentioning every single integer. It would start 0, minus 1, 1, minus 2, 2, minus 3, 3, minus 4, 4, and it would keep on going like that. I'd like a formula for that sequence. Well, here's a formula for the sequence. C sub n will be defined via this piecewise definition depending on the parity of n, whether n is odd or even. If n is odd, then the nth term will be negative n plus 1 over 2, and if n is even, then the nth term is just n over 2. And I'll start with the index 0. And this will give me this sequence, right? The 0th term, well, I plug in 0, 0 is even, 0 over 2 is 0, and that gives me the 0. When I plug in 1, 1 is odd, so I get negative 1 plus 1 over 2, that's negative 1. When I plug in 2, that's even, so it's 2 over 2, that's this 1 here. When I plug in 3, 3 is odd, so it's negative 3 plus 1 over 2, that's negative 2. And it just keeps on going like that. There's another way to think about this. To say that I've got the same quantity of dots and squares is really to say that there's some method by which I can pair off the dots and squares so that every square gets a dot and every dot gets a square. And once I've paired them off like this, it's very believable that there's the same quantity of dots and squares. Well, something similar is going on with non-negative integers and all integers. If I just take a look at the non-negative integers, I perhaps want to show that there's the same quantity of non-negative integers as there are just all integers. And to do that, I just have to tell you some method for pairing off non-negative integers with all the integers. And that's exactly what this sequence does, right? It assigns to 0 the number 0. It assigns to 1 the number minus 1. It assigns to the index 2 the number 1. To the index 3, the sequence assigns the number negative 2. To the index 4, it assigns the number 2. To the index 5, it assigns the number 3. To the index 6, it assigns the number 3. And it will keep on going. And eventually, right, we've ended up pairing off every single non-negative integer with every single integer. And that really means that there's the same quantity of non-negative integers as there are all integers. That should really give you pause. That sounds impossible, right? Think about some physical object, some finite object like coffee beans. If I've got some coffee beans, but then I take some away, now I've got fewer coffee beans. But the collection of all integers is different. If I start with all the integers and just take away the negative integers, I've got the same quantity of things. Why does that work? Well, one definition of an infinite quantity is a quantity that needn't get smaller even when you take something away.